Identifying minerals. So geologists rely on several simple tests based on a mineral's chemical and physical properties. Some of these tests include the crystal form, if you can see it, the luster, the hardness of the mineral, the cleavage and fracture, or how the mineral breaks, texture, streak, which is the color in powdered form, the color itself, the density, the specific gravity, which is another way of measuring density, and then other special properties. So we're going to talk about all of these individually here. So crystal form. So some minerals are easily recognized by their crystal shapes. So halite, for example, or table salt, forms nice perfect cubes. So you get these nice perfect cubes of salt. Quartz forms six-sided crystals with pointy ends, so crystals like this. However, this characteristic is rarely used by itself since most minerals do not form large perfect crystals, because remember, they form in crowded spaces, so these crystals tend to grow together, so you don't get these nice, big, fully formed crystals. But if you can see the crystal form, it is a good way to identify minerals. So luster. Luster refers to the way the mineral reflects light from its surface. Our first major division is metallic versus non-metallic. So you pick up a mineral, you look at it, and does it look like a metal or not? So sphalerite up here is metallic in luster, and then cinnabar down here is non-metallic. So metallic luster has a shiny surface that reflects light like chrome, so it looks like a metal. Silver, gold, copper, galena, which is a lead sulfide, and sphalerite, which is zinc sulfide, all have metallic lusters. Now, metallic luster doesn't mean that you're dealing with a pure metal. So just because it looks like a metal doesn't mean it's a pure metal. It could be something else. Like fool's gold, which is an iron sulfide, looks like gold. Galena looks like silver. It's a shiny, silvery metal looking mineral, but it's lead sulfide. And then sphalerite up here again looks like zinc sulfide, or it looks like a metal, but it's not pure metal. Non-metallic luster can be described as dull, pearly, waxy, silky, or earthy, and this is a very subjective kind of description, because a lot of people aren't going to agree. Is it earthy, or is it waxy, or is it glassy, or whatever? There's a bunch of different lusters you could have here, and it's pretty subjective. So sometimes it's good if you list two or three that it might be. So some examples of luster. So you got metallic, you got submetallic, which is shiny, usually not silver or gold looking, but maybe black and shiny or something like that. So we call that submetallic. Adamantine, which kind of looks like diamond or glass. Resinous, kind of looks like plastic. Vitreous, pearly, greasy, dull, earthy, silky. You can also have glassy, waxy, soapy, etc. Sometimes the luster is how it looks, and sometimes the luster even goes into texture. So sometimes the texture and the luster, texture is how it feels. But sometimes those terms cross each other, like greasy. It can look greasy. It can also feel greasy. Same with soapy or waxy. But again, luster is how the light reflects off of it, what it looks like. So hardness is a measure of how easily mineral can be scratched. This is one of the most useful and reliable tests for mineral identification. So developed by Frederick Mohs, the Mohs hardness scale is based on 10 common minerals. So talc being the softest is a 1, diamond being the hardest is a 10. Softer minerals can be scratched by harder minerals. So what you do is you take one mineral and you try to scratch the other one. If you can scratch it, then the one you're trying to scratch with is harder. Like for example, this looks like granite. It is harder than this glass plate because this is scratching it. If it couldn't scratch it, then this would be softer. Here you're able to scratch this with a thumbnail, so this is softer than a thumbnail, which is about a 2.5 on the Mohs scale. Glass has a value of about 5.5, so it's a good place to start to see if the sample will scratch glass or not. So it's a good place to start. If it scratches the glass, then it's harder than 5.5, so you're looking in the upper half of the scale. If it doesn't scratch the glass, it's in the lower half of the scale. So trying to scratch glass is a good place to start. So the scale looks something like this. So Mohs scale of hardness. Again, we have diamond, which is 10. We have corundum, which is aluminum oxide, which is a 9, actually, and that's sandpaper. So it was basically what they use on sandpaper. Topaz, which is an 8. Quartz, which is silica dioxide, is a 7. Also, a porcelain streak plate is a 7. Feldspar is a 6. A steel file or a good steel knife is about 6.5. Apatite's a 5. Glass is 5.5. So what we have over here is the minerals. So if you have a kit with the minerals, you can use these. You also have common objects over here. So fluorite is a 4. Iron nail is about 4.5. Calcite's a 3. Piece of copper, like a penny, an old penny, not a new penny, because new pennies aren't really copper. But copper is about 3.5. Gypsum is a 2. Fingernails about 2.5, and then talc is a 1. So you can kind of basically what you do is you kind of get an idea of the hardness by what will it scratch. So for example, feldspar would scratch anything below it. So anything below feldspar could be scratched by the feldspar. Nothing down here would scratch the feldspar. Okay, so that's how you do it. You test one against the other. Now, if you can, you kind of try to scratch one and then try to scratch the other. But whichever one does get scratched is the softer one. Whichever one does not get scratched is the harder one. So using Mohs scale. So begin by trying to scratch glass, which is a 5.5 with the unknown mineral. If it scratches the glass, try to make a streak on a streak plate. If it does leave a streak, its hardness is between 5.5 and 7. If it does not leave a streak, then it's harder than 7, which is the hardness of our streak plate. If it does not scratch glass, then try scratching the mineral with your fingernail. If you cannot scratch it with your fingernail, its hardness is between 2.5 and 5.5. If you can scratch it with your fingernail, its hardness is less than 2.5. So what you have here is you have a streak plate, your fingernail, and a piece of glass, and you can kind of use those to break this down into quarters. So you have below 2.5, you have 2.5 to 5.5, 5.5 to 7, and then above 7. So you kind of break it into these 4 bands to get a rough idea of how hard a mineral is. If a sample appears to have different minerals, test several different spots. So if you can obviously see different minerals, test those different spots to see if you can figure out what minerals there may be. Now, how minerals break? Cleavage. So arrangement of atoms determines how minerals will break. So breaks occur along planes where bonds are weak. So if you have weak bonds, you're going to have breaks occur there. So cleavage describes a mineral that splits relatively easily and evenly along one or more flat planes, like the halite here breaks along 3 different planes and forms cubes. Mica has one very distinct plane that it will break along. So you use the number of planes and the angles formed between them for identification. So for example, again, mica forms flat sheets, so it has one cleavage plane. Halite forms cubes. It has 3 cleavage planes at 90-degree angles. So you can kind of use that and get an idea of what mineral you're looking at. Does it have 1, 2, or 3 cleavage planes? What are the angles between those, etc.? And you can get an idea of what the mineral is. These aren't cut this way. These will break this way. If you hit this with a hammer, it will break along these flat planes. So cleavage, this is not something that's done artificially. These just happen naturally, these breaks. Now, some minerals break unevenly along jagged edges, and we call this fracture. So this occurs when the atoms are tightly bound. So obsidian, for example, is a volcanic glass, and you get these jagged fractures when you break obsidian. So fracture describes minerals that break with rough or jagged edges. Conchoidal fracture is a special case where arc-like patterns resembling clamshells are formed at breaks. So things like obsidian. This is a conchoidal fracture. Flint, jasper, and chalcedony are examples, as is obsidian. So fracture, you don't get nice, even, smooth breaks. Okay, so some examples. So halite, again, has cleavage planes. It's got 3 cleavage planes at right angles to each other, so it forms cubes. Quartz just has fracture, so it just breaks at different jagged patterns. And then you have conchoidal fracture in this flint here, so you see these sort of arc-like patterns as the flint is broken.